Hello, everyone. My name is Dallas Dominguez.
And my name is Girish Krishnan.
We are students from the Electrical and Computer Engineering Department. Today, we're going to be discussing a topic we covered for our final report for Intro to Visual Learning that has to do with future video prediction based on past frames. The ability to predict the future based on past experience and intuition is a fundamental trait that we as humans use to survive each day. We see the best examples of this phenomenon in sports, where split-second predictive decisions can mean the difference between a victory, a loss, or even an injury. It almost looks like magic when a combatant can completely read their opponent's move and perfectly counteract it. So we propose the question, for a sport such as fencing, is it possible to teach a machine at some level to be able to predict the movements of combatants? The Generative Adversarial Network offers a powerful framework for future image predictions. GANs have a strong generative capability. The adversarial training process in GANs encourages the generator to continuously improve its generated samples by learning from the feedback of the discriminator. And GANs can also learn to capture complex data distributions. One of the techniques that we learned in our course was optical flow, which is the motion of objects between consecutive frames of a sequence. This is caused by relative movement between the object and the camera.
So here's a high-level description of our neural network architecture. So we have a generator, which consists of an encoder and a decoder, and each of them have multiple convolutional layers. We also have a discriminator, of course, and again, which also consists of multiple convolutional layers, as well as batch norm layers.
So the data set we're using is the HMDB Human Activity Recognition dataset, which is composed of around 7,000 clips from 51 action categories like jump, kiss, laugh, and each category contains about 101 clips. So there's a file called fencing within this database, and it contains 30 testing videos and 86 training videos, which are in AVI format. We trained our network on these videos, but first and foremost, we had to properly format them. So the videos are in AVI format, as you can see here, but we needed to convert them all individually to a series of JPEG images, each video being a file containing the frames of the video in JPEG format. So in terms of performance, we did two metrics, which are the inception score and the FID. Inception score measures how well the images can be classified by an inception model and the diversity of the generated images. And we can see that our model has an inception score that gradually increases over 500 epochs. So GANs are notoriously challenging to train, and they can be prone to instability. The oscillations in the inception score that we see here could be a symptom of the generator and discriminator struggling to find a stable equilibrium during training. On the right, we see the FID, which measures how similar the features, like mean and covariance, of the real image and the generated images are. The lower the FID score, it indicates a better quality and more similar distribution. We can see that our plot lowers as it goes along the 500 epochs, which implies that we have a better FID score, so we have better performance.
Now let's look at the generator and discriminator loss plotted over 500 epochs. As you can see that there are lots of fluctuations as there is constant competition between the generator and the discriminator. Now let's very briefly look at the training progress over our epochs. So in this video, we have the generated fake images over each epoch. So as you can see in the earlier epochs, the generated images have very poor quality. So, a lot of them are barely recognizable. And as the number of epochs increases, we can see that the generated images become gradually more realistic. And our final result, which comes around epoch 500, is shown over here. So now let's look at some of our results when it comes to predicting a single subsequent frame. So on the bottom right, we have the original video from the HMDB dataset. If you consider just one of the frames in the video, the images plotted right over here show the current frame, the actual next frame, as well as the predicted next frame based on our model. As you can see, the predicted next frame is actually pretty realistic. And here are a few more examples showing the current frame, the real next frame, as well as the predicted next frame. So here's one more example, and here is another example. What if we want to generate multiple frames, not just a single frame, or essentially predict a video? So now let's look at the results of our model predicting multiple frames and generating a short video predicting what's going to happen next in a game of fencing, for example. So here we have the actual video on the left, alongside the predicted video shown on the right based on our model, after we give it just one input frame. The overall motion patterns are quite similar, and the overall color scheme is also quite similar, although as you can see, the image is definitely blurrier. Let's look at a few more examples. Here's another example where overall the left and right motion of the players are captured, even though, again, the clarity is not very great. And lastly, here's another example. Now let's discuss the results. So looking at the accomplishments, we can see that we were able to train a GAN using commonly available personal computers. So for example, I trained this GAN using my MacBook. And it is possible for us to generate fake images that look reasonably realistic. So as you can see on the right, as some examples. We also got a reasonably low resolution prediction of a few frames after we passed in one input frame. Looking at some of the limitations and improvements, firstly, we use just one input frame to predict the next frame. A good solution would be to experiment with a recurrent neural network or an LSTM, which is one example. We also have dataset limitations because our videos we use for training are just about 1 to 3 seconds. They're really short videos, and the image size is also very small. We only use a 64x64 image, which is why the image looks very blurry. We also have a feedback effect, which is common with FutureGAN implementations, where the amount of error compounds as you keep predicting more frames because you're using the predicted frames as an input to predict subsequent frames. And that's it for our presentation. And here is our GitHub repository with all our code and documentation. Thank you.
Thank you.